So, good evening, everyone, and welcome back to the third session of NPTEL online course, Drug Delivery Principles and Engineering. Today will be, as you all know, we have been discussing some old assignments, last year assignments, and today, as this is the third week, we'll be discussing week 3 assignments. Let me just share my screen. Can you guys see the presentation in slideshow mode? One of you can just unmute your mic and let me know.
Yes, ma'am.
Yeah, thank you. So has anybody gone through the material for week 3? Do you guys know what has been discussed in this week? So that I know if we have to discuss in detail or not. Yes, anyone? If not, we'll just go through a quick recap of what has been discussed in this week. So we have been talking about this controlled drug release systems, one of which is reservoir systems. And in this week, the week has started with something known as orifice devices, which we'll discuss in detail as that is part of one of our questions in this assignment. Also, some other systems such as non-erodible systems has been discussed in which the drug is encapsulated in a polymer membrane and the polymer does not bioerode. The drug usually diffuses out as and when, and that's where we can have a controlled system. Another system is something known as bioerodible systems in which you have your drug encapsulated in a polymer. Now that polymer is biodegradable, meaning that as time goes on, it will start degrading. So in this system, the drug will not come out of the system because of diffusion. It will eventually come out when that polymer starts degrading slowly. Next, hydrogels have been discussed. Hydrogels are one of the most important matrix systems in drug delivery. So what are hydrogels? They are made up of hydrophilic polymers, and because they are made up of very high hydrophilic molecules, polymer chains, they tend to absorb water and they swell. And although having hydrophilic polymers, they are insoluble, meaning that their cross-linking network is very strong. It is usually physical or chemical cross-linking. Apart from that, they have this hydrophilic chains. So, and these hydrogels can be customized. They can be made bioerodible or non-bioerodible based on the application. And they are used in various different fields such as tissue engineering and drug delivery. So how can you use a hydrogel in drug delivery? Let's say you take a particular material which you know can form hydrogels very well. You encapsulate your drug inside that, and in the dry state, the pores which are formed because of these polymer chain entanglement are very, very small. So your drug cannot diffuse out of the system. Now, once your this hydrogel matrix comes in contact with water, it's going to swell. It's going to form bigger pores, and that's where your drug will start leaching out. That's how you can make a drug delivery system using hydrogels. In this week material, further more details about hydrogels are given, such as characterization of hydrogels. Certain parameters have been discussed, such as porosity, tortuosity, and molecular weight. And also types of hydrogels has been discussed. There are various types of hydrogels broadly classified into physical and chemical hydrogels. Also, you can customize hydrogels to have stimuli responsive drug release. Let's say, for example, I want my drug to be released at a very particular location in my body where the pH is suppose, let's say it's 5. So what I'll do, I'll make the hydrogel at, let's say, pH 7, and once it goes at pH 5, I'll choose certain polymers which swell at pH 5 when they absorb water, and that's where I can have a site-specific drug delivery. Do you guys have any doubts in the discussed material? If not, we can just move on towards the assignment. Shall we move on towards the assignment then? You have to unmute your mic and let me know so that I can understand where to stop. Guys, am I audible?
Yes.
Just keep on switching in between these two screens. I cannot see you people when I'm in the slideshow mode. So instead of sending me a text or raising your hands, you can just unmute your mic and let me know if there's a problem. So I'll move on towards the assignment. So can you see the first question displayed on the screen? Okay, I'll read out the question. The question says, what is not correct about reservoir systems with orifice type of implants? We have to choose two correct options, and the options are they can greatly increase circulation of the drug in the body. The device can be excreted in urine and sweat. Drug release generally follows first order kinetics. Example is Procardia XL tablets. The drug finds its way out of the orifice. The drug can be released by a swelling control mechanism. I'll give you guys some time to think about this. If you have read about the reservoir systems with orifice, you will be able to answer quickly. If not, we'll discuss about what exactly the system is. But before that, if anybody wants to volunteer, you can go ahead.
One answer is the drug is excreted in the feces, not in the urine and the sweat.
Exactly, exactly.
So
So we have to choose
that's
false options.
yeah. That one is I know one. The second one is not correct.
Yeah, the second, so the right answer for this question is option second. We need two correct options. Anybody else wants to give a try?
Option 3.
Third option, ma'am.
Okay, third option. Yeah, so we have three people have given me two different options, so we can arrive at the right one. Yes, so the correct answer is the device can be excreted in urine and sweat is the false option, and drug release generally follows post order kinetics is also false. Let's look at this reservoir systems with orifice. If you have gone through the material, you'll see a similar slide. So this is how reservoirs with orifice look like. Let me just get a pointer. Yeah, so you have something like this. So it has a semi-permeable membrane that is permeable to only water. And you have a certain hole here. If you see, this is the actual tablet, and you see this smaller hole in the middle, that's where the drug is going to be released out from. So now before operation, this is how it looks like. During operation, as and when water enters, we have something known as an expandable polymeric compartment that will start expanding, and that will push the drug out of this small hole here. So that is the whole point of this reservoir with orifice. And as you can see in this example, if you have this drug nifedipine in its native state, when no other polymer system is used, if you administer this drug orally, it has a half-life of only 2 hours. Instead of that, if you pack it up in this tablet and then you administer it orally, because it is now having a very smaller surface area to be released from, the drug half-life has been increased from 2 hours to 24 hours. And since this tablet can be administered orally, it gets excreted in its feces and not in sweat and urine. There's another type of reservoir. So this is like a customizable thing. You can make any shape you want. It just has to be applicable. So this is another system of reservoir system with orifice. Here you have the semi-permeable membrane that is permeable to water, and you have your drug loaded in this impermeable reservoir, meaning the drug cannot go out from this blue and yellow region, and the drug can only be moved out from this very small pipe you see, and then you have a flow moderator. Now whenever this device, if you can implant this device wherever you want. In this example, they are working with mice model, so they have implanted it in this region. As and when water enters this device, it will push this drug out. Since this is an impermeable reservoir, the drug has only one place to go out from, that is from this small pipe. So this is where the flow moderator is, which can control how much amount of drug is released out from this implant. So by doing this, you are just increasing the drug half-life and you can have a controlled drug delivery. Is this clear? Does anybody have a doubt here? Have you guys understood this? Okay, then if no doubts in this, we'll move on towards question two. The second question is, there is an assertion given to us. When a controlled release formulation is placed in biological medium, it immediately releases some quantity of drug as a bolus. And the reason for this is this burst effect is attributed to the time history of the device, with older formulations allowing diffusion of some quantity of the drug to the surface. Now we have to choose whether both of these are true, both of these are false, the assertion is false, or the reason is false. Read through it for a time and for time being and let me know the answer if anybody wants to volunteer. I'll wait for your response.
Both are true, the assertion and the reason.
Okay, we have one answer where both are true. Anybody else wants to give their opinion? Okay, we can discuss this now. Yeah, the answer is correct. I cannot see your name, sorry, because I'm in the slideshow mode, but you were correct. So let's look at this. So we have this controlled release formulation where our a drug is loaded in this polymer membrane and this polymer is non-biodegradable. Now what happens is this drug will start diffusing and it'll be diffused in this polymer membrane until we have given it a aqueous environment. So let's look at what lag and burst effect is. This happens because of the time history of the device. Let's say you have your device made and it is kept in storage because there is no immediate application for it, and after some time somebody buys it from you. That's when you see a burst effect. Why does that happen? Because when your polymeric device was in storage, this drug has diffused out from this system and it has collected on this outline here. So that is why your membrane is now saturated with the drug. And once you start its application, once it's injected in the body, it comes in contact with this aqueous medium. And that's why a large amount of drug will come out before the steady state follows. So that's where you see this burst effect, where ideally in this graph, if you take a graph of drug release versus time, you should be getting a linear curve here which starts from its origin. Instead of that, what you'll see is at time zero itself, a large amount of drug will be released and then your steady state will follow. This is the burst effect. Next effect is lag effect, where if you have made the device and you immediately start its application, in that case, your drug will need some time to be saturated in this membrane. As a result, you'll initially have a lag effect because as time goes on, no drug will come out because it's taking time to be saturated in the membrane. And after that, your steady state will follow. So the question is, when a controlled release formulation is placed in biological medium, it immediately releases some quantity of drug as a bolus. This is the assertion. And as we discussed right now, the reason for this is the burst effect is attributed to the time history of the device, the older formulations allowing diffusion of some quantity of the drug to the surface. Is this clear? If you guys have any doubt at any point of time, you can stop me right here and ask away. If not, we can move ahead. I'm sorry, I'm seeing this message very late. Sujata, are you able to hear me now? Am I audible to the rest of you?
Yes, ma'am.
Okay. Yeah, let's move on towards the next question. Avidine conjugated to polymeric biotin is it a physical hydrogel, complex coercivate, chemical hydrogel, inotropic hydrogel, photolinked hydrogel, or enzyme linked hydrogel? Any guesses?
Option one.
It's a physical hydrogel. Okay, any other answer? No? Yeah, the right answer is physical hydrogen. So physical hydrogels are polymer networks which are, so as I said, there are different types of hydrogels. Some of it can be physical hydrogels, some of it can be chemical hydrogels. In physical hydrogels, the polymer networks are held together by neutral or ionic bonds, or it can be a molecular entanglement, or it can be a play of secondary forces such as hydrogen bonding. Now, contrary to this, chemical hydrogels will have a very strong covalent bonding. Now, one example of physical hydrogels can be physical gels which can be formed from biospecific recognitions. So, as you know that biomolecules, if they're very specific to each other, they can form a very strong hydrogen bonding. They, there need not be any covalent bonding for them to stay together. It can be a play of secondary forces. So, one such example is avidin with a polymeric biotin. So, that's why avidin conjugated to polymeric biotin is a type of physical hydrogen. Clear? Shall I go ahead? Okay, let's see the next question. Porosity in non-erodible matrix systems can be measured by which technique? There are two correct options: AFM, DLS, osmometry, surface plasmon resonance, liquid leaching experiments, or electron microscopy, followed by image analysis. Straightforward question, nothing to think about. If you guys have gone through the material, it should be easy. Anybody trying to answer?
Electron microscopy for image analysis is one.
Yes. Okay, we have one answer. Any other answer?
Liquid leaching experiments.
Liquid leaching experiments. Okay, we have two responses. Anybody else? Let's look at it. Yeah, both of you are correct. Both of these techniques have been used to calculate the porosity in non-erodible matrix systems. So non-erodible matrix systems are something like this. You have your drug diffused in the polymer, and as time goes on, the drug will start diffusing out of this because there is less concentration outside and a lot of concentration inside the polymer matrix. So porosity is the calculation of how big or small your pores are in this polymer matrix. So this can be done using density and volumetric measurements, liquid leaching experiments, and image analysis. Straightforward answer. Let's read the fifth question. Which of the following two statements are false for bulk hydrogen? Hydrogels are three-dimensional hydrophilic polymer networks capable of swelling by absorbing large amounts of fluid. They have predictable or known swelling rates, insoluble due to physical or chemical crosslinks, which provides a network structure and physical integrity. They are soluble in water. They have low burst effects. They are used in contact lenses and suitable for all delivery routes. We have to choose two false statements. Any guesses?
4 and
Suitable
7,
for
ma'am.
Both of you at once, one by one?
suitable for all delivery routes.
Okay, that is one answer. Anybody else?
They are soluble in water.
Okay. Okay, we have two options. Anyone else wants to give a try? No more responses? Okay, yeah, both of these answers are correct. They're soluble in water and suitable for all delivery routes. So this is how we can define a swelling control matrix. That is the hydrogel. You have your drug dissolved in polymer in dry state. Once it comes in contact with water, it is going to swell. And because the pore size now increases, your drugs can easily diffuse out of the system. The advantages of this system are low burst effects, because there is no membrane here. In previous case where we saw the burst effect, you have this non-erodible membrane which gets saturated. There is no such thing happening here, so you don't have any burst effects. You have known or predictable swelling rates. So to calculate its swelling rate, what you can do is you can put this polymer in water. Once you manufacture this, you can just make some preliminary experiments where you put this polymer in water and you calculate how much amount of drug is being diffused out. That's where you can at least predict about the swelling rates. Reformulation of vehicle is not necessary for different drugs. Some of the disadvantages are it has generally short release periods, because once it swells, it cannot contract now because it's always in contact with water. So most of its drug will come out in a very short time. And it's not suitable for all delivery routes or targets, because let's say you inject this in your bloodstream, and when you made this polymer, let's say it's of dimension of somewhere around 3 micron, and once you inject it, since it comes in contact with the water which is flowing in the blood, it's going to swell. Let's say it swells to somewhere around 10 micron from a 3 micron particle. Now your capillaries are of somewhere of the same dimension of 10 microns. They are going to be clogged. So if you clog this, you might run the risk of cardiac arrest. So because of this, it's not suitable for all delivery routes. And as I said, even though they're made of hydrophilic chains, they are insoluble in water. So both of these options are wrong, that they're soluble in water and they're not suitable for all delivery routes. Am I clear? If you guys have any doubts, you can ask. Any doubts? If not, we can go ahead. Next question is, what is heat capacity of a system? More of has to do with the definition of heat capacity. Anybody knows the answer?
Third option.
Third option.
Okay, I have two responses. Others want to try? Let's see. Yeah, heat. So essentially, heat capacity of a system is the heat required to increase the temperature of a system by 1 degree Celsius. So heat capacity is a system phenomenon and not a surface phenomenon. Just keep that in mind when you'll be dealing with such questions. I'm assuming no doubts in this question. I'll move on towards the next. When the drug loaded is greater than its solubility, which of the following is true for drug release from scaffolds? The interface between dissolved drug region and dispersed drug region moves into the interior as a front. The interface between dissolved drug region and dispersed drug region moves into the exterior as a front. The interface between both these regions remains stationary, or the system will not behave dynamically.
Option 1.
Option 1. Okay. Any other response? People can just unmute the mic and let me know if they have other answers. Okay, yeah, the correct answer is the interface between dissolved drug region and dispersed drug region moves into the interior as a front. You were right, whoever answered. So let's look at some of these possibilities. So as you know that the scaffold system, in a scaffold system, we can have four different cases. First case is we can have a dissolved drug. which then diffuses through the polymer. Second case is we can have a dispersed drug, which is again diffusing through that polymer. Or we can have a dissolved drug that is diffusing through the channels in a polymer. Or we can have a dispersed drug that diffuses through the channels. Now let's look at the terms of what exactly does dissolved and dispersed mean. In the case of dissolved, it is the drug loading amount is lower than the solubility limit in the polymer, which means that your drug is completely soluble in the polymer and that's where it's going to diffuse from the polymer. On the contrary, there is something known as dispersed. In dispersed case, we have your drug loading is an amount which is higher than the solubility, which means that the drug is at a supersaturated concentration inside the polymer. It's going to form particles. It's not completely soluble in your polymer. Now, the question is asking us when the drug loaded is greater than its solubility, that means it's in a dispersed uh, condition. What happens to this interface? So this is the case 2 we are dealing with, where your loading of the drug is higher than its solubility. So to study the kinetics, how the drug is released from it, we have something known as a Higuchi model, where we assume that the drug is uniformly suspended, there's no gradient, there's no swelling or shrinking of this material, and it looks like something like this. So let's say you have a system like this. This membrane is impermeable and your drug can be released only from this particular side, and you have this drug at a very high concentration here, which means it's in a dispersed state. Now once this comes in contact with water, your water is will start going inside, and that's where, because of the action of water, some amount of the dispersed drug is going to dissolve. Let's say it starts dissolving here, because that is the maximum amount of water where it can be in contact with the water. So this is where it will start dissolving. After some time, let's say at time t, this interface is going to start moving inside, because initially your dissolved drug will be here. As time goes on, your dissolved drug will be here, because then there's nothing here. Your dispersed drug has started to move outside. It will first dissolve in this membrane and then it will go out. So as time goes by, this interface, the interface between your dispersed drug and dissolved drug, is slowly going to start moving inside. So that's what the question is asking us. So the correct option is the interface between dissolved drug region and dispersed drug region moves in the interior as a front. Is this making sense? Am I clear? Do you guys have any doubts about this? Has everyone understood this phenomenon? Shall I go ahead?
Yes, yes, madam. Yes, yes.
Thank you. Okay, the next question is type of hydrogels that can polymerize after injecting into the body are called physical cross-linking hydrogels, chemical cross-linking hydrogels, in situ cross-linking hydrogels, neutral, photo-linked or enzyme-linked hydrogels.
In situ cross-linking hydrogens.
Okay, we have one answer. Anyone else?
Sir, in situ.
Okay. Others want to give it a try? I'll wait for a while for you to respond if anyone wants to. Okay, let's see. Yeah, both of you are correct. The right answer is in situ cross-linking hydrogels. So what are these? These are cross-linked at the site where a physician has a syringe and we'll inject both these polymer chains. Let's say your hydrogel is made of two different polymer chains, and it will cross-link only under certain conditions which are formed inside the body. Let's say at temperature 37, which is your body temperature. and it forms a hydrogel inside the body. So this polymerization trigger can be anything. It can be time. Let's say your two polymer chains require certain amount of time to react with each other, or it can be temperature, or it can be pH. It has its own advantages and disadvantages as well. The disadvantage mainly being it may diffuse throughout the body. Let's say you inject it, and before the two, because your body has a lot of fluid, the injected material will start flowing everywhere. So let's say before the polymer chains could even get time to interact with each other, it's lost. So this might not have a very high efficiency, and going ahead, you don't have any control of shape. So you don't know how these polymer chains are going to react with each other. They might form a sphere, they might form a very weird shape, and we as a result, we don't have any control over the drug that can be released from this, as we don't know what shape it's going to form. Clear? If no doubts in this, I'll move ahead. The next question is, what is true for bioerodible matrix delivery systems? And we have to choose two correct statements. Degradable, more patient compliant. Non-degradable, byproducts of degradation will always be highly toxic. It can achieve first order with surface eroding polymer devices. Answers?
Degradable, more patient compliant.
Okay, that is one answer. We have to choose
Option 4, ma'am.
option 4. Okay. Any other response? I'll wait for a minute or two. Okay, let's look at the answers. Both of you are correct. Uh, these bioerodible matrix systems are degradable, they're more patient compliant, and they can achieve first order with surface eroding polymer devices. So whenever you see this questions like this where you have to choose two correct statements, make sure that you answer both of these. Because right now I'm getting one response, one correct answer from two different people. So make sure you choose both the options. So, so bioerodible systems are like this. Your drug is dispersed, as we have discussed previously as well. Your drug is dispersed in this polymer, and this polymer is bioerodible. So as time goes on, at time t, let's say, your polymer is going to start shrinking, it's going to start degrading, and your drug that is encapsulated inside this polymer will start diffusing out. So the advantages of such system are, as it's degradable, it's more patient compliant, because in the case of non-bioerodible systems, what you have to do is you once you manufacture that polymer system, you have to implant it inside the patient body, allow the drug to do its action for, let's say, for a duration of 1 or 2 years. After that, since they are non-biodegradable, you have to perform another surgery where you have to remove that implant from the body. Now, patients will be more compliant if you have only one surgery instead of two surgeries. So in that case, its advantages, the bioerodible systems. Also, it can achieve zero order with surface eroding polymer devices. Now, the disadvantages are release kinetics is often difficult to control, because although you can have systems in place where you can have a quality control, you can try putting these bioerodible systems in vitro and you can check how they are getting released. But still, once you inject it into a patient body, you don't have a control on its release kinetics. You don't know how it's going to release, how faster it's going to degrade. Also, Since it's getting degraded, the byproducts of this degradation may cause biocompatibility problems. Now, this is not always the case. It depends from polymer to polymer. It also depends from a specific immune response. We don't know how a polymer is going to react, how a patient's body is going to react to one particular polymer. So that's about this biodegradable systems. Do you guys have any doubts? Anyone? If not, I'll take up the last question. So this is the last question for today's assignment. In a membrane reservoir system with 5 microns of membrane thickness, 5 mg of drug is released after time t. If the desired release of drug is 1 mg, what should be the thickness of the permeable membrane? We have to report the answer in micrometers. So I'll give you guys some time to solve this and let me know once you're ready. If not, we'll anyways discuss the solution. Anybody has the answer?
Around 25, ma'am.
Okay, we have one response where the answer is 25. Anybody else? Anybody else wants to give it a try? If not, we'll discuss the solution. Okay, let's look at the solution. Yeah, the right answer is 25. If your answer falls in between this range, a very narrow range, 24.8 to 25.2, it's correct. So let's look at it step by step. So we have been given the length of the thickness of the reservoir system and the drug released from it. And we, in case the drug release is lowered from 5 mg to 1 mg, we have to calculate how much the thickness should be. So if you have gone through the lectures, you'll see we have a formula for which sums up the release kinetics of membrane reservoir systems, which is something like this. Now here, since it's the same drug used in both the cases, and it's the same surface area as well, just the thickness of the reservoir system is going to change. Therefore you can just assume we don't need to know the value of these variables. Your A, that is the surface area, D, that is the diffusion coefficient, K, that is your partition coefficient, and Cs is the solubility of your drug in the membrane. We don't need to know these values. So what you can do is you can write this expression, write two different expressions for two different cases, and just take the ratio of these two. If you do that, just put in the values. The only value we don't know is the thickness in the second case, and once you calculate that, you'll get The answer is 25 micrometer. Is this making sense? Are you guys getting this? Let me know if you have any doubts on this. So this is just an oversimplified example of how we can have a control over the system. If you want less drug to be released, all you have to do is you have to increase the thickness to 5-fold, and that's how you can customize these devices for actual applications. People have any doubts in this particular assignment we discussed, or if you guys have any doubts in the previous assignments, we can discuss them, or in the new current assignments. Anybody trying to say anything?
Yes, ma'am. Ma'am, can you just repeat the fourth question again?
Repeat which one?
Fourth one.
Okay, I'll just go through all the questions. You can stop me wherever you have doubts. So this is for people who joined a bit late. Let's go over the questions quickly, one by one. First question was, what is not correct about reservoir systems with orifice type of implants? And the answer was, the device can be excreted in urine and sweat, and the drug release generally follows first order kinetics. Both of these are false because these devices look something like this. They are either of a tablet kind or a capsule kind, and they are injected orally, so they'll be excreted out in the feces and not in your urine and sweat. Also, since the drug release is just a matter of how this device is made, so it is not going to depend on how much, so the drug release is not going to depend on how much drug is there in this compartment. So it essentially follows first order kinetics. Next, the question was, we have an assertion where when a controlled release formulation is placed in biological medium, it immediately releases some quantity of drug as a bolus. And the reason for this is this burst effect is attributed to the time history of the device, where older formulations allowing diffusion of some quantity of the drug to the surface. Both these statements were true because in these polymer systems, we always observe something known as lag and burst effects, which is because of the time history of the device. If the device is used after a long time after it was made, because it was kept in storage, the drug is quickly going to saturate this polymer membrane. And if it's used after a lot of time, it's going to quickly come out, and that is going to lead to a burst effect, which was the answer for this question. On the other hand, we have something known as lag effect. If the device is immediately used as soon as it's manufactured, the drug is going to take some time to get absorbed into this polymer membrane, and that's why it's going to have a lag effect. Next was avidin conjugated to polymeric biotin is a type of, as you guys guessed correctly, it was a physical hydrogel. These are some of the points to remember for physical hydrogels, and this avidin with polymeric biotin was one such example. Next was porosity in non-erodible matrix systems can be measured by which technique? The right options were liquid leaching experiments and electron microscopy followed by image analysis. Porosity is one of the parameters of how you can characterize these non-erodible matrix systems. Porosity generally means the amount of pores or the dimension of the pores in a non-erodible matrix system. Next question was, which of the following two statements are false for bulk hydrogels? The right answer was they are soluble in water and they are suitable for all delivery routes. Both of these are false because they are insoluble in water. That's why we use them for drug delivery. And they are not suitable for all delivery routes because as they change in dimension, we don't have a control of how they are going to swell. And as a result, if you accidentally inject it, and it may cause problems with clogging of the capillaries. Next was, what is heat capacity of a system? We know by definition that it is the heat required to increase the temperature of any system by 1 degree Celsius. Next question was, when the drug is loaded, drug loaded is greater than its solubility, which means essentially the dispersed case. Which of the following is true for drug release from scaffolds? We saw that for this case where the drug is dispersed throughout the polymer and the drug is being released from only one side, the interface between the dispersed drug and the dissolved drug starts to move in the interior of the front. So the correct option was the interface between dissolved drug region and dispersed drug region moves into the interior as a front. Next question was the type of hydrogels that polymerize after injecting into the body are called in situ cross-linking hydrogels. Pretty straightforward. If you have read through the material, it's clear to understand. Then the question was what is true for bioerodible matrix delivery systems? We had to pick up two correct statements, which are they are degradable and hence they are more patient compliant and they can achieve first order with surface eroding polymer devices. And the last question was a short numerical where we have this membrane reservoir system with 5 microns of membrane thickness in which 5 mg of drug is released after time t. If we want the drug release to be 1 mg, what should be the thickness of the polymer membrane? And we solve this using this formula where the amount of drug released is related to the time and thickness of the membrane in this equation. We just take a ratio, put in the values we know, and then we can get at the right answer. Is there any other question you want me to discuss? Somebody had said they wanted something to be discussed, right? Which question was it? So, Kristen, if I'm pronouncing this right, you want me to post the recording of this meeting, right? So this will be uploaded on YouTube. I guess you guys will get the link for this from the NPTEL team. Are you getting the link for the previous two sessions?
No,
You did not get that, is it?
no, we didn't.
Okay. In the next meeting, I'll give you the link of all these three sessions. Let me check if I have it now. Okay, apart from the link issue, anybody else has any doubt in the assignments we discussed right now or the previous ones or any other doubts in the lecture series? Let me know if there is anything else to be discussed or if you missed any question, we can go over the question once again.
The fourth one.
Fourth question. Okay.
Yeah.
Okay, let me share my presentation again. This one?
Yes, ma'am.
Yeah, so the question is porosity in non-erodible matrix systems can be measured by which technique? So the answer was liquid leaching experiments in electron microscopy followed by image analysis. Sorry? You're not audible.
Thank you.
Yeah, you got that right?
Yes, ma'am. Yes.
Yeah, it was mentioned in the slides as well. So I'll anyways be sharing this material with you. Any other question? Okay, somebody wants me to explain eighth question. Okay, give me a second. Okay, this is the eighth question. Darshan, I'm assuming you have this doubt. The type of hydrogels that polymerize after injecting into the body are called, so this system of making hydrogels is known as in situ cross-linked hydrogels, where you suppose your hydrogel is made of two different polymer chains. You take those two in syringes and you inject it inside the body. Now, because of the certain conditions, you can choose polymers depending on the trigger. Let's say you want to make a polymer based on the temperature of your body. So you can formulate these chains at, let's say, room temperature, and they are going to react with each other at 37 degrees Celsius, which is your bodily temperature. So once you inject them, they are going to cross link at and when they come in contact with each other. That is known as in situ cross linking hydrogels at the site of the injection. That's where they're going to form this complete hydrogel. Darshan, is it okay? Am I clear in this? Yeah, sure. Welcome. In the next session, I'll give you the links of all the previous sessions as well as this session. If anybody else has any doubt, we can discuss. I'll wait for a few minutes. Thank you. Thank you, Vithi. If not, we can stop the meeting here and I'll see you guys next Tuesday for the discussion of week 4 assignments.
Thank you, ma'am.
Thank you. Others don't have any doubt, then I'll stop the meeting. Shall we stop here? Okay, then bye guys. I'm going to stop this meeting. Let me know if you have any doubt in the next session. Bye bye.